Hello, I welcome you all to the course of Advanced Algorithm Analysis. Our week number 11 is about search trees. In week number 10, we talked about heap sort algorithm. We saw its analysis, the different operations that we can perform on the heap, and other related topics. In this week, we are going to study a very important topic that is known as search trees. Here is a brief agenda for today's presentation. We will start our discussion with the objectives, the outcomes that you will learn at the end of this lecture. After that, we will formally start the search trees with a very important type of tree known as binary search tree. We will also see and cover different operations that we can perform on a binary search tree, like how to insert a node, how to delete a node, how to search for a node in a binary search tree. We will also analyze different operations like the insertion, deletion, and searching operations in order to analyze the binary search tree. After that, we will study some other types of search trees. For example, one of them is AVL, another one is red-black tree, the third one is AA tree, and finally Splay trees. So this is a roadmap for this week lecture. Let us start with the objective. I believe that at the end of this week, you will be able to understand the concept of binary search tree. And you will also be able to learn the different operations that we can actually perform on a binary search tree, like insertion, deletion, and searching. In addition to that, you will also get an introduction, a know-how of some other types of search trees like AVL, red, black, AA, and Splay trees. Let us start with the binary search tree. All of the data structures that we will see in this lecture, they are search trees. Data structure, as you know, is a way of organizing the data. And you may be familiar with different type of data structures. For example, link, list, array, graph, stack, queue, hash tables, etc. All these are data structures which present different ways or for organizing the data. Tree is also an example of a data structure. And there are different types, different categories of trees. One of the most important one is the binary tree, in which each and every node must have at most two children nodes. At most mean 2 or less than 2. Then the binary tree can be subcategorized into different type of trees. We have studied some of the binary trees like complete binary tree, full binary tree, skewed binary tree, etc. One of the important type of binary tree is known as binary search tree, which is an important data structure. In order to understand the concept of binary search tree, let us start with an example. Here we have a tree. This is an example of a binary tree. Why? Because every node has at most 2 children. In other words, you can say that no node has more than 2 children. 28 has no node. They are example of leaf node. 89 has only 1 node. 32 has 2 nodes, and so on. This is an example of a binary tree. Binary trees, binary search trees, or any other search tree, they are important because you can use them to implement different type of structures like order maps and ordered dictionaries. We will not go into the details of maps and dictionaries, but in one line summary, a map is actually a collection of key value entries in which each value is associated with a distinct key or a unique key. You can say that in a map, every element is recognizable by a unique key. On the other hand, the dictionary concept is a bit different because in a dictionary, multiple values may share the same key value. Okay, coming back to the binary search tree, for example, this tree, which is a binary tree, is given to us, and somebody asks us to search the key, the value, the element, for example, 58 in this binary tree. To do so, we can use any of the traversal algorithm. If you revise the concept of data structure, you have different methods to traverse a tree. Traversing is an operation which means visiting each and every node of the tree or every element of the tree. And there are different ways to traverse a tree. For example, pre-order traversing, in-order traversing, and post-order traversing. Okay, to find 58 in this binary tree, you can actually do a traversing. You can apply a traversing algorithm to visit each node and then compare the search item, which in this case is 58, with the data stored in the node. However, this operation, searching of this item in this tree, this operation could require us to traverse or visit a large part of the binary tree. So the search would be very slow because we need to visit each node in the binary tree until either the item is found or we have traversed the entire binary tree and the item doesn't match to any node. Okay, so this is a slow process because we do not have any criteria for our search. And this searching is like an arbitrary linked list where we must start our search at the first node. If you have a list of items given and you are asked to find 58 in the list, the first thing that you need to do is to compare it with the element at the first location, and then with the second, and then with the third, and so on. You are also familiar with linear array and linear search. What was the disadvantage of linear array? If you want to find an element in a linear array and the element is not present in the list, still you will need to compare that element with each and every element of the array. So same is the case here. If we want to find 58 in this tree, we have to compare this element with each and every node in the tree. Okay. You have to compare 58 with the root node 78. If they are equal, the search is successful. The item is present in the tree. If that is not equal, then you will have to compare it with 32, then 89, 46, 28. On the other side, you have to compare it with 60, 98, and 53. At the end, you will conclude that the item is not present in the tree. You have to perform n comparison, for example. In the binary tree, in this figure, the search is very much slow. Now, let us consider another binary tree. In this binary tree, the data in each node follow a standard way, and that is that each node is larger than the data in its left subtree and smaller than the data in its right subtree. Take an example of this node, for example. It is actually the value, this value is actually greater than the left subtree and smaller than the right subtree. Or in other words, you can say that the subtree is less than the root while the right subtree is greater than the root node. 50 is less than 60 while 70 is greater than 60. Now consider 30. It has no left child, but the right child must be greater than the parent, that is 46. And same is the case with 50. The left child must be smaller than the parent, and the right child must be greater than its parent. Now, suppose you want to search for the same item 58 in this binary tree. As before, we must start our search at the root node. We compare 58 with 60. Because 58 is not equal to 60, and 58 is also less than 60, it guaranteed that 58 will not be in the right hand side. So you do not need to search this hand side because it is less than the root node. Therefore, 58, if 58 is in this binary tree, it must be in the left subtree, because we know that all the elements on the left hand side are smaller than 60. That is the property of this tree, that everything on the left side must be smaller, and every node on the right hand side must be greater than this root node. Okay. Now we follow the left hand side of this tree in order to search for the 50. Once you compare it with 60, it is less than 60, then you have to come here. Now compare 58 with 50. Is it equal? No. Is not equal? Is less? No, it is not less. Is it greater? Yes, it is greater. So that means that you do not need to search the item on this left hand side, because here everything is less than the 50. You have to come here and search for the item 58. Then you have to compare 58 with the parent. Now the parent is this one, which is also 58. So 58 is equal to 58. And our search is successful in this case. Okay. This example shows that every time we move down to a child, we eliminate one of the subtree of the node from our search. First, we ignore this right hand side. Then we ignore this left hand side. So at every step, we are actually eliminating one of the subtree of the node from our search. If the binary search tree is nicely constructed, mean is a balanced tree, the search is very similar to the binary search on arrays. Did you remember? In case of array, we studied two different types of algorithm, linear search and binary search. Linear search was not an efficient algorithm. Binary search was much more efficient, especially for large data set, because the running time is log n, and that is much more efficient, and we do not have to compare the element that we want to search with each and every element of the array. So in this case, searching for 58 in this tree is like searching an element by using binary search in the in the array. Okay. Now this tree that you can see here is a binary tree, a special type of binary tree, and this tree is actually known as binary search tree, or BST in short. Now let us define binary search tree. We now learn the concept of binary search tree from the example, but here is the formal definition of a binary search tree. Suppose you have a binary search tree, or suppose you have a binary tree that has been represented by capital letter T. As we know that binary tree, it is possible for a binary tree to be empty, but a general tree can never be empty. So the first case is whether to check whether the tree is empty. If it is empty, then it is a binary search tree. If it is not empty, then it must uh, have it must has to follow these principles, these 4 principles. Any binary tree which is not empty and which satisfied, if it is not empty and it satisfied all these rules, then we can say that it is a binary search tree. What are these rules? The first rule is that the given tree must have a special node which is known as the root node. In this example, the root node is 60. So the first property is that the given tree must have a special root known as the root node. Second property is that the tree T must have 2 sets of nodes, L and R. L stand for left, R stand for right. Mean left child and right child. Or you can say they are the subtrees, left subtree and right subtree of this special node root node. So the first property is that there must be a root node, and the second property is that it has 2 sets of nodes or subtrees represented by L and R respectively. Third property, which is very much important. The key, the value, the element in the root node must be greater than every other node in the left subtree, and it must be smaller than every key in the right subtree. And we saw it here. 60, you see, it is actually greater than the left subtree, and it is actually less than the right subtree. Okay, so it must be greater than the left subtree and less than the right subtree. And last property, that everything beneath this must also be a binary search tree. Mean as a whole it is a binary search tree, but again the subtree, the left subtree must be a binary search tree, and again this subtree must also be a binary search tree, and again this subtree must be a binary search tree. Similarly on the other hand side. So these are the properties of a binary search tree. To put things in a simple way, binary tree is a tree where the value of the parent node, each parent node, must be greater than the value of its left child, but it must be less than the value of its right child, or you can say left subtree and right subtree. So this was the basic definition of a binary search tree. The binary search tree actually satisfied the search order property. What does it mean? It means that for every node X in the tree, the value of all the keys in the left subtree are smaller, as in this case, all the keys on the left hand side, they are smaller. Suppose this is X. And all the keys in the right subtree, they are larger than the key in the X. You can see we have one node, but the value here is larger than 7. Now these two trees, both are binary trees, but let us see whether they are binary search tree as well or not. The tree shown in figure A is actually a binary search tree. Why? Because everything on the left is less than the root and everything on the right is greater than the root. Again, this parent is greater than the left and it is less than the right. Again, this parent is less than 3. So this is a binary search tree. What about the second tree given in B? Let us see the properties. It is a non-empty tree. Okay. It has a root node. That's good. The value at the root node must be greater than everything here on the left hand side. So is less than 2. Okay. Is less than 1. Okay. Is less than 5. Okay. Less than 3. Okay. But not less than 8. Which means it does not satisfy the property of the binary search tree. Right hand side is okay because 9 is greater than 7. But here it violates the property of the binary search tree. So that is not a search tree and not a binary search tree. In summary, the binary search tree property implies that all the items in the tree can be ordered consistently. And if you remember the in-order traversal of a tree, if you do the in-order traversal of a tree, it will give you the item in sorted form. What does it mean? Let's suppose we have a tree, which is a binary search tree, as in case of 1, and perform the in-order traversal of this binary tree. In in-order traversal, we first visit the left child, then we visit the parent of this left child, and then we visit or traverse the right child. Let us apply this formula, this procedure on this tree. So this is our parent node. So first we need to traverse its left child. Come here. Stop. Now this is the parent, but it has a left child, which is 1. So process this left node first. That is 1. Okay. After processing the left child, you have to traverse, access, visit the parent. The parent is 2. So traverse it. Then come to the right child. Once you come here, stop here. Now this is your parent. Do not process the parent. First you need to process the left child. So the left child here is 3. Process it. Then come to the parent node again. After left, you have to traverse the parent, which is 5. Okay. After traversing, go back to the parent, already processed. Go back to its parent node, which is 7. Left has been processed. Now it's time to process the parent. The parent is 7. After processing of parent, come to the right child. The right child again is a parent which has no left. So process this and no right. So stop here. This is the inner traversing of a binary search tree. Once you perform the inner traversing, it will always give you ascending form. You see 1, 2, 3, 5, 7, 9, they are in ascending form. So this is a very important property of the binary search tree, that if you apply the inner traversing, it will yield items in a sorted form. And one more thing, important thing, is that this property also does not allow duplicate values. That is not possible. So in conclusion, binary search tree is an excellent data structure for storing data, especially if the data is in the form of a map, a key value pair, or it is in the form of a dictionary. Okay, students, now we learn about the binary search tree. It's time to shift our focus to operations. You can perform different operations on any data structure. Some of the key operations that you can actually perform on a binary search tree as mentioned here. The first operation is that you can search for an element in a binary search tree. And we will see it in details in a moment. Then another operation is insertion. You can add a new item to the tree. In a similar way, you can also delete an existing item from a tree, binary search tree. It is also an important operation. In this lecture, we will focus on these three operations. We will see examples of each of these operations in details. But there are also some other types of operation that is not going to be the focus of this lecture. For example, you can find the height of a binary search tree. You can calculate the size of a binary search tree, total number of nodes or elements in a binary search tree. You can also find the labels, total number of labels in a binary search tree. And also you can traverse, visit, access each element of the binary search tree. You can find the minimum value as well as the maximum value in a binary search tree, another operation. Or even you can copy the content of one binary tree into another binary search, into the content of one binary search tree into another binary search tree. Let us see the search operation in details. Searching is a basic operation, and we perform searching on a linear array as well as we have seen the algorithm of binary searching. Okay, so search operation, search is the binary search tree for a given item, and as we just saw, the output of this operation is true if the item is present in the tree, and it is false or unsuccessful if the item for which we are looking that is not present in the tree. In order to search for an element in binary search tree, you have to start your search operation at the root node. It means that first you have to compare the item with the root node. If it is equal, then the search is successful. If it is not equal to the root, then you have to check whether the given element is less than the value of the root node or it is greater than the value of the root node. If it is less than the value of the root node, it's understood that you have to search for the element in the left subtree. But if it is greater than the root node, obviously you have to go to the right hand side to search for the element. And then you have to repeat this process for the next node. And at the end, if the search item is in the binary search tree, our search will end at the node which will contain the search item. Otherwise, the search ends at an empty subtree. Let us consider an example of the search operation. Our first example is very simple. We have given a binary search tree. We know it is a binary search tree because it satisfied all the properties. Remember the properties? If the tree is non-empty, which is a non-empty of course in this case, then there must be a root node. So we have a root node, and the value at the root node must be less than all the values on the right hand side, and it must be greater than all the values on the left hand side. So this is an example, a perfect example of a binary search tree. Let us search the element 6. Compare the given element with the root. If it is equal, then the search is successful. If it is not equal, then it must be less than or greater than the value at the root node. So after comparison, we came to know that 6 is actually less than the root node. So it means you do not need to search the element on the right hand side. Come here and look for it in this left subtree. Now compare this element with the parent. It is 2. Is 6 equal to the parent node? No. 6 is not equal to 2. So it means the given item is either less than 2 or it is greater than 2. So after comparison, we came to know that it is actually not less than 2, but it is greater than 2. So there is no need to search the item here. You have to search the item in this location. Now compare 6 with this parent node. If it is equal, the search is successful. Is 6 equal to 5? No, it is not equal. Then the item is either less than 5 or is greater than 5. 6 is greater than 5. It means there is no need to search the item on the left hand side. You have to search it on the right hand side. But on the right hand side, there is no other node. We have reached to an empty subtree. The tree is searched completely, but the item is not present in the tree. So it means the search is unsuccessful because 6 is not present in the tree. Second example, now let us search for another value, that is 17. The first thing is that you have to compare this element with the root node. The value at root node is 25. Is 17 equal to 25? No. Is it less than 25? Yes. It means that you have to skip half of the tree the first time. There is no need to search there because all the values there are actually greater than 25. So come on the left hand side. Search the item here. First you need to compare it with the parent node, that is 13. Is 17 equal to 13? No, it's not equal. Check whether it is less than 13 or greater than 13. So 17 is greater than 13, which means there is no need to search the item here as well. Next, you have to compare 17 with the parent node 20. Is it equal? No. Is it less than? Yes. So it means there is no need to search on this right hand side. The item is somewhere here if it is present in the tree. It could be here. Now compare the 17 with the next parent node, that is 16. Is it equal? No. Is it less? No. Is it greater than? Come here. Now compare 17 with 19. Is 17 equal to 19? No. Is it less than 19? Yes. So the item must be here. Now compare 17 with this parent. Oh, 17 is equal to 17. We have found the item. So our search in this case is successful. So this is how we actually search a binary search tree. This is the standard process for searching for an element in a binary search tree. Let us see a short animation about searching a binary search tree. The tree is given to us. Our pointer, this is actually implementation, but we will ignore the code as we will be focused only on the animation. But we have a pointer variable which currently point to the root node because our search always started at root node. So compare the item that you want to search with the root node. For example, we are searching for a key value 32. So first thing, you have to compare the item to the item with the root. Okay, so 32 is not equal to 37, so it is less than 37, which means you have to search for the item in the left subtree. Now the pointer is pointing to the parent and the value here is 24. Compare 32 with 24. Is it equal to 24? No. The value is not equal to the tree. So it must be less than or greater than, either less or greater than 24. After comparison, we came to know that the value is greater than 24. So it must be on the right hand side. So move the pointer to the right hand side. Now this is like a recursive process. We are applying the same process again and again. Compare 32 with this parent node, okay, to which the RT is currently pointing. After comparison, we came to know that 32 is actually equal to 32. That is, the record for which we were looking is actually this one. Okay. So after finding the element, you have to move the pointer back. This is something for which is related with the implementation. So we will not go into the details, but you have to move the pointer to the root node from where we actually started. So in this case, our search is successful and 32 was found in this tree, binary search tree. So this was our first operation that we can actually perform on a binary search tree. We also have another operation which is known as insertion operation. To insert a new item in a binary search tree, first we search the binary search tree and find the place, the location where the new item is to be inserted. As duplicate values are not allowed in the binary search tree, so our search must end at an empty subtree, because we always have to insert the item at the empty, you can say the leaf node. And then after finding the location, you have to insert the element in a straightforward way. Let us see an example. We have a binary search tree given, which is here, and we are asked to insert the new item, the new key value 6 in this binary search tree. Let us see how the insertion will occur. First, go to the root node. The value there is 7. 6 is less than 7, so it means we have to insert it in the left subtree. Come here, compare it with 2. 6 is greater than 2, so it means we have to insert it somewhere here. Next parent 5. 6 is greater than 5, but it is actually the node which has no right subtree. So this is the actual location where you can insert the item 6. Let us see another example of insertion. Suppose we started from an empty tree. The first node that you want to insert in this case will become the root node. So if you insert 31, it will be the root node of the binary search tree. Next, you are asked to insert 16 in this one node binary search tree. So you have to compare 16 with 31. As 16 is less than 31, so we have to insert it on the left hand side. After insertion of 16, we are asked to insert 45 in this newly constructed binary search tree. For insertion, first you have to compare it with the root node. As 45 is greater than 31, so you have to come to the right hand side. As we have no further nodes here, so 45 will be inserted here. Next, after insertion of 45, we are asked to insert another node, that is 24. Repeat the same process. First, compare 24 with the root node. Is it less than 31? Yes. So come to the left hand side. Compare it with 16. Is it less than 16? No. Is it greater than 16? Yes. So you have to come to the right hand side. As we have no subtrees here, so 24 will be inserted here in the appropriate location. Next, we are asked to insert 7. Compare it with the root node. Less than or greater than? 7 is less than, so come to the left hand side. Now compare it with 16. Is it less than 16 or greater than 16? 7 is less than 16, which means it will be inserted in the left hand side. As we do not have any further subtrees, so 7 will be inserted here. And then we are asked to insert 19. Repeat the same process. Compare it with 13. Is it less than or greater? So 19 is less, which means come on the left hand side. Now compare with 16. Oh, 19 is greater, so come to this hand side. Now compare with 24. As 19 is less than 24, so we have to insert it here like this. And finally, let's insert 29 in this binary search tree. Compare with root. Less, come here. Compare with 16. Greater, come here. Compare with 24. Greater, come here. As we have no more nodes, so that is the appropriate location for inserting 29. So this is how we actually perform insertion operation on a binary search tree. Now let us see animations. In this animation, we will see how we actually insert a new node into a binary search tree. Let us start. First, our pointer will point to the root node. Like insertion, we have to start from the root node. Suppose we are asked to insert the value 30 in this tree. Once you come to the root node, then you have to compare the value that you want to insert with the value that is stored at the root node. As we want to insert 30. As we want to insert 30 in this node, in this tree, so 30 is less than 37. So we have to visit the left subtree. Once you come to 24, repeat the same process. Compare the given value 30 with 24. Is it equal? No. Is it less? No. Is it greater? Yes. So you have to come to the right subtree. Again, repeat the same process. Now this is your parent node. Compare the given item 30 with the item to which the pointer is pointing, that is 32. Is it equal? No. Is it less? Yes. It is less than 32. So it must be come to the left subtree. As we do not have any subtree on the left hand side, so we have to insert the new item here. Link it with the parent node and then go back. So this is how we actually insert an item, a new item in a binary search tree. After the insert operation, we have the final operation that is known as the delete operation, which means to remove an element from a binary search tree. So let us study the delete operation. Actually, the search and insert operations, they are a bit simple. The delete operation is the hardest operation, the most difficult operation. Once we have found the node to be removed, to be deleted from the binary search tree, we need to consider several possibilities. In the delete operation, the problem is that the removal of a node from the tree may disconnect parts of the tree. If that happens, we must carefully reattach the tree and maintain the binary search property as well. Means after deletion of a node, it is possible that the tree become disconnected. So in that case, you must have to reconnect the tree in such a way that the property of binary search tree remains intact. To perform this operation, first we search the binary search tree to find the node that we want to delete. And then after deleting the desired item, if it exists in the tree, the resulting tree must be a binary search tree. Let us consider an example. The example that you see on the screen actually shows a binary search tree. We have to consider several cases, several possibilities. Case number 1. Suppose we want to delete a node from this binary search tree, and the node that we want to delete has no left and right subtrees. That is, the node to be deleted is actually a leaf node. You know, in tree terminologies, a leaf node is any node that has no child. In this case, in this tree, 32 is a leaf node. Let me highlight them. Leaf node, 45 is a leaf node, 77 is a leaf node, and 57 is also a leaf node. Because each of these nodes do not have any kids, any child. So if you want to delete 32, if you want to delete 57, if you want to delete 77, or if you want to delete 45, that will be considered as case number 1. In case number 1, the node to be deleted has no left and right subtrees, mean the node is a leaf node. Second case, the node that we want to delete from the binary search tree has a non-empty right subtree, which means that left subtree is empty while right subtree is present. In simple word, if you want to delete a node but it has a left subtree, it has a right subtree, then that case is considered to be case number 2. For example, the left subtree of node with information 40, for example this one. If you want to delete this node 40, then this is case number 2. Why? Because the left subtree is absent. Another example, if you want to delete this 75, that is an example of case number 2. Why? Because the left subtree is missing. If you want to delete 70, that is considered to be case number 2. Why? Because the left subtree is missing. And so on. So in case number 2, actually the node to be deleted has no left subtree. And case number 3 is actually opposite of case number 2. In this case, case number 3, the node that we want to delete has no right subtree, or you can say left subtree is present, but the right subtree is not present. The node to be deleted in this case has no right subtree. That is, the right subtree is empty, but it has a non-empty left subtree. One subtree must be present in case number 2, and also one subtree must be present in case number 3. The present is the difference between these two is that whether the tree that is missing is left or right. Example of case number 3 is that, for example, you want to delete node number 80. You see, this is case number 3 because the right subtree is absent. In a similar way, if you want to delete 48, then there is also an example of case number 3 because the right subtree is missing. Okay. These two are the examples of case number 3. And finally, the most difficult case is case number 4. Why it is the most difficult case? Because the node that we want to delete has non-empty left and non-empty right subtrees. In other words, the node that we want to delete has the left and right subtrees available. And the example of the fourth case is the node, let's suppose we want to delete 50. So now you can see left subchild is present and right subchild is also present. For example, you want to delete 35. In this case, left subtree is also present and right subtree is also present. Okay, let's suppose you want to delete 60. Left is present, right is present. That is case number 4. Let us see example of each case. First, in this example, you can see a tree, a binary search tree. This is actually the same tree. Suppose we want to delete node number 45 from this binary search tree. The first thing is that you have to search the binary tree. So we compare it with the root node, is less, compare with 50, is less, compare with 30, is greater, compare with 35, greater, compare with 40, greater, compare with 48, oh, it's less, come here, then we find. We search the binary tree and arrive at the node, which contains 45. As this node is a leaf node. Remember, case number 1. The node that we want to delete has no left and no right subtrees. That is the leaf node. And this is the example. 45 is a leaf node. So it is an example of case number 1. How we can actually delete this node? Because this node is a leaf and is the left child of its, then we can simply delete this node. And after deleting this node, you can actually see the tree like this. Now 48 has no left child. So this is the situation before delete, and this is the situation after deleting the leaf node 45 from the binary search tree. This was an example of the first case. Example of the second case. Remember, in the second case, we actually want to delete a node that has a non-empty right subtree. It means that in case number 2, the given node that we want to delete must have one child or one subtree, and that is the left subtree. Sorry, the right subtree. So this is our case number 2. Suppose we want to delete the node 30. You see, in this case, this node that we want to delete actually has a subchild, right subchild, and that is 35. The problem is that once you locate this node, if you delete this node, then what is going to happen with the rest of this tree? It will be disconnected from the above tree. So we need to select a node from this node which will replace any node that we have selected, will actually replace or will take this place. So the node that we actually want to delete has a non-empty right subtree. If we delete this node, then these two trees will be disconnected. So we need a mechanism in order to maintain the connectivity as well as the property of the binary search tree. So this is a bit tricky because 30 is actually a left child of its parent. We make the link of the parent node point to the right child of 30. Let me repeat. We are going to delete the 30 from this binary search tree. However, the 30 has a non-empty right subtree. If you delete this node from here, the two trees will be disconnected. So we need a mechanism to maintain the connectivity as well as the binary search tree property. To do so, we can see that 30, and this 30 is actually left child of 50. Once we delete this child, this node from here, which is actually the left child of 50, then this will be replaced by this 35, which is actually the right child of 30. So you can see the situation after deletion in this figure B. We have deleted the node 30 and that location has been replaced by its child, there is 35. You can see the rest of the tree is same, 32, 40, 48, 45. So this is actually how you can delete a node which has a non-empty right subtree. Remember case number 3? That is actually opposite of case number 2. Because here, if we want to delete a node that has a non-empty left subtree, then that will be considered as case number 3. For example, let us delete node 80 from this tree. As you can see that it do not have a right subtree, but it has a left subtree which is present here. Now the problem is that if you delete this node, it will disconnect these two trees. So we need a mechanism to re-establish the connection and also maintain the binary search tree property. In this case, as you can see that this is actually the right child of the parent node 70. After deletion of 80, this place will be filled by the left child of this node 80, and you can see the left child is 75. So 75 will be shifted to the location of 80. The child will take the location of the parent now, and you can see it here. 75 has taken the location of its parent, that is 80. These were two cases where the node that we want to delete has either the left subtree present or the right subtree present. Now the most tricky case, the most difficult case of deletion is case number 4. Why? Because here the node that we want to delete actually has both the child present. For example, 50. If we want to delete 50, then you can see that the node with information 50 has a non-empty left subtree and a non-empty right subtree present. Here we first reduce. In case number 4, we have to reduce this to either case number 2 or case number 3. But the question is how it is done. To be specific, suppose that we want to reduce it to case number 3 as just we saw here. There is the node to be deleted has no right subtree. For this case, we find the immediate predecessor of 50 in this binary search tree. And we know that the immediate predecessor of 50 is actually 48. How we know that? Two methods. First method is simple. If you are considering a node to take place of the parent in the left subtree, then it must be the value that is greatest, largest in this subtree. So you can see we have 30, 35, 32, 40, 48 and 45. What is the largest value in all these nodes? It's 48, which means you have to select 48, which will be selected, and it will take the location of 50. That is if you are considering the left subtree. Suppose you want to consider a node from the right subtree. In this case, it must be the smallest. So we have two nodes, 53 and 57. What is the smallest value? 53. So 53 will come and take the location of the parent. This is the first solution. You can take a node from the left subtree and you can take a node from the right subtree, up to you. If you are taking a node from the left subtree, it must be greatest value. While if you are considering a node from the right subtree, it must be the smallest value in all the nodes. In this particular case, we have selected 48, the left subtree. So you can see after deletion of the node 50, the situation is like this. 48 will take the location of 50, as you can see here. But now you can see that 48 has a child, and the child is the left child. So this child will take the location of the parent. Case number 2, case number 3, that is simple. And you can see 45 take the location of the parent. Again, this is the first solution. Let us see the second solution. Second solution is like this. First, you have to do in-order traversing. Again, let me rewind. In in-order traversing, we first traverse the left subtree, then the parent node, and then the right subtree. What is going to be the in-order traversal of this tree? This is parent, go to the left. Parent, go to the left. Now traverse this left child, which is 30. After left, come to the parent. The parent is 50. Traverse it. Then come to the right side. No. Wait. This is parent. Go to the left. Now this is parent. Go to the left. Now this is parent. Go to the left. We do not have left, so process parent 30. Now come to the right. Stop here because it is parent now. Do not process it. Come to the left side. Now this is parent. As it do not have the left, so process the parent. Come to the right, no child. Okay. Now come to the parent and process it. 35. After the parent, come to the right child. Now this is parent. We do not have left child, so process the parent. Then come to the right child. Again, this is parent. Do not process it. First process the left child, which is 45. Then process the parent node. And then the right, so we have no right. Go big. Come here. 50, which is the parent now. Process it. Now come to the right child. Again, stop here. Now this is the parent. No left, so process it. 53. Now come to the right child. There is 57. Process it. Bake. Now this is the parent. Process the parent. Come to the right side. Now this is the parent. We do not have left child, so process the parent. There is 70. And then come here. Now this is the parent. Go to the left. Now this is the parent, but we do not have the left child, so process the parent. And then process the right. Go back. We have processed the left, so process the parent. And we do not have right. Now see which node that we want to delete. That is 58. So if you want to delete 58, you have two options. Option number 1, 48 can take the location of the parent. Second option, 53 can also take the location of 50. And that is what I mentioned you here. If you want to delete 50, then you have to select the largest here. So the largest is 48, and you can see from the in-order traversing. Or you have to select the smallest from here. We have two nodes, and the smallest is 53, and you can see from here as well, 53, right? So you have two methods to delete a node that has both the childs present. You can do the in-order traversing and then replace the node that you want to delete by the predecessor or by the successor. Or the second method is that select the greatest value in the left subtree or the smallest value in the right subtree. Okay, if this is not clear to you, let us consider a second example. In summary, you have, if you want to delete a node that has both the child or subtrees present, then you have two options. You can either take the largest value in the left subtree, or you can take the smallest value in the right subtree. Both are acceptable. Okay, for example, you want to delete the node 32, which has both the children or both the subtrees available. In this case, you have two options: select the greatest here, or select the smallest value here. So now I am going toward the second option, to select the smallest value in the right subtree. So you have three nodes, 48, 42 and 46. The smallest value is 42, which means 42 will take the location of 32. But wait, this node also has a child, which means case 2 or case 3. But that is simple. The child will take the location of the parent. So 48 now has a children with 46, and 32 will be replaced with 42. This was how we can actually delete a node that has both the left subtree and right subtree available. We have studied three operations on binary search tree. Let us come towards the analysis of binary search tree. As we saw in merge sort algorithm, binary search algorithm, quick sort algorithm, all are log n because they are based on the concept of the tree. Same is the case with the binary search tree. For binary search tree, we can actually do analysis in different ways. One of the very common way is to analyze the search operation, then analyze the insert operation, and then analyze the delete operation. Let us start with the analysis of the search operation. The analysis of the running time of the search operation or the search algorithm is simple. Why? Because the binary tree search algorithm, it actually executes a constant number of operation for each node it traverses in the tree. Each new step in the traversal is actually made on a child of the previous node. First you have to traverse the parent, then the child. That is, the binary search algorithm is performed on the nodes of a path of a tree, for example T, which is represented by T. It actually starts from the root and goes down one level at a time. Thus you can say that the number of such nodes is actually bounded by height of the tree. It is h plus 1, where h is actually height of this tree. In other words, you can simply say that we spent a constant time big O1 per node that we encountered, that we visited. So in summary, the search method runs O h time, where h is again height of the binary tree T. In this figure, the running time of searching in a binary search tree is given. The figure uses actually standard visualization shortcuts for viewing a binary search tree, as it has been represented by a big triangle, and this is actually the path from the root to the desired node. This is like a zigzag line. The height of the tree can be as large as n. N is the total number of nodes, but we expect that it is usually much smaller than n. So the best or the best case is like the height of this tree is, as usual, as we know, is log n plus 1. And we would hope that in most of the cases h would in fact be big O log of n. So in summary, the analysis of the searching is actually give us an equation which is log n. Let me repeat the analysis of searching. We have a tree represented by a triangle. The tree has different label, and on every level we have at most 2 nodes. So the analysis of the running time of the search algorithm, actually the algorithm execute a constant number of operations for each node it traverses in the tree. Each new step in the traversal is made on a child of the previous node. You know, this is the parent, this is the child. Then this will become the parent and this will become the child. And we know that the height of the tree is actually represented by h. So if you are searching for a node, you have to compare it with the root node, which will take a constant amount of time, that is big O1. If it is, for example, greater than the root node, then you have to search it in the right hand side. Again, big O1. If it is less than, then you have to search it on the left hand side. Again, big O1. If it is greater, then this side, less this side, greater this side, and so on. So the total height is h, which means big OH. As we spend big O1 time per node that we encounter, so the search method runs in big OH time, where h is the height of the tree. The height of the tree can be as large as n, which is the total number of nodes, but we expect that it is much more smaller. In the best case, we can do for the height h, that is log of n plus 1. And we would hope that as it is the best case, so in most of the cases, h would in fact be big O log of n. There is a proof for this equation, but we will not go into the details of the proof. In analysis of insertion, actually the insertion algorithm is analogy to that of the searching algorithm, means both do actually the same thing. Because in the searching, we start from the root node. In the insertion, we also start from the root node. And the number of nodes visited is proportional to the height of the tree, which is represented by h. And in the worst case, since we spend big O1 time at each node that we have visited, so the implementation and analysis of the insertion algorithm is actually the same. The running time is the same as that of the running time of the searching. And same is the case with deletion. The analysis of the removal algorithm is analogy to that of the insertion and the search algorithms. Like the previous two cases, we have to spend big O1 time at each node that we have visited. And in the worst case, the number of nodes visited is proportional to the height h of the tree. So you can say that the removal method will actually runs big OH time, where h again is the height of the tree. This was analysis of the deletion. What about analysis of the binary search tree algorithm? We saw analysis of the insertion, analysis of the deletion, and analysis of the search operation. But what about analysis of the BST algorithm itself? Actually, we have two different possibilities. One is the case of the balanced tree. The other is the case of a completely unbalanced tree. The cost for finding an element and inserting an element in the binary search tree is actually the depth of the node found. And similarly, the cost for removing a node is the depth of the node being removed. Or in the case when this node has two children, for example, the depth of the node with smallest value in its right subtree. Thus, in the worst case, the cost of any one of these operations is actually the depth of the deepest node in the tree. This is why it is desirable to keep binary search tree balanced with least possible height. If a binary tree is balanced, then the height of the tree of n node is approximately log of n. This is the summary, the important point to remember. If you have a balanced binary search tree, then its height will be approximately log n. However, if the given tree is unbalanced, balanced tree is like this, where the number of levels of each node is actually the same, or at most one difference is there. On the other hand, if we have a skewed tree like this, then it is a completely unbalanced tree. So if a tree is a completely unbalanced, like the skewed tree, it could be right skewed or left skewed, or even you can consider a linked list also an example of an unbalanced shape. So if the tree is unbalanced, then the height of a tree will actually be a linear function, that is n. So you can say that a balanced binary search tree will in the average case have the performance of log of n, theta log of n. But if it is an unbalanced binary search tree, then the operation in the worst case is going to be a linear function, that is theta n. Okay, and there is also a proof for it, but we will not go into the detail. In summary, you can say that in the best and the average case, the analysis of the binary search tree is n log of n. But in case of the unbalanced binary search tree, if the tree is unbalanced, then in worst case the analysis is theta n. Okay, this was about the first type of search tree, which is known as binary search tree. It is an efficient algorithm, especially if you want to search for an item, or if you want to print the element in a sorted order. Beside from BST, we also have some other type of search trees, and one of them is known as AVL tree. While the binary search tree is a simple type of tree, it is simple to understand, it is simple to implement, and it is simple to perform different operations on the BST. And it is also an efficient algorithm, especially if the tree is balanced. However, the possibility of being unbalanced is a serious liability for BST. As we just see that if the tree is unbalanced, then the performance is degraded. To deal with the unbalanced tree situation, there are techniques for organizing a binary search tree that will guarantee good performance. Okay, two examples are the AVL tree and another tree is Splay tree. These trees, AVL and Splay, they are there to improve the worst case performance of the binary search tree. Okay, before going to explain the concept of AVL tree, let us understand the concept of a perfectly balanced binary tree. We have used the word balanced in the analysis of the BST tree. Let us see what is a balanced binary tree or a perfectly balanced binary tree. Actually, a perfectly balanced binary tree is a tree such that the height of the left and right subtrees of the root are equal. The figures show a perfectly balanced binary tree. Let's suppose the tree is represented by T, which is a binary tree. And suppose X be a node in this tree. If this tree is perfectly balanced, then from the definition of the perfectly balanced tree, it follows that the height of the left subtree of x, for example, this is x, must be same as the height of the right subtree of x. Suppose x is this node, then the height of the left subtree must be equal to the height of the right subtree. Suppose x is this node, then the height of the left subtree must be equal to the height of the right subtree. This is an example of a perfectly balanced binary tree. Now come towards the definition of the AVL tree. The tree is actually named after the initials of its inventors, Edison, Whiskey, and Landis. So A from here, V from here, and L from here. That is called the AVL tree. This AVL tree is the oldest known balanced search tree because it was invented in 1962. Sometimes it is also known as height balance tree. And this was the first balanced binary search tree which was invented. It is a binary search tree that has an additional balance condition which was not in the BST. So an AVL is actually a binary search tree like the BST with these two properties. The properties are that the height of the left and right subtrees of the root differ by at most 1. Here we saw perfectly balanced binary tree where the height of the left subtree and right subtree were equal, were same. But in case of AVL, the height of left and subtree must be equal. However, if there is a difference of 1, then it doesn't matter. But greater than 1 is not acceptable. Mean if the left subtree is at height, for example, at height 1, and the right subtree has a height 2. Okay, that is acceptable. A difference of 1 between the left and right subtree is acceptable, but not more than that. If the height of one, for example, left subtree is 1 and the height of the right subtree is 3, then that is not acceptable. There must be a difference of at most 1, mean 1 or less than 1, which is 0. Second property, that the left and right subtree again will satisfy the property of the AVL tree, means they are also AVL trees. Okay, the left and right subtrees are also AVL trees like this. If this is an AVL tree, then this must be an AVL tree, and this subtree is also an AVL tree. Let us see some example of AVL trees. A single tree itself is AVL. This is also AVL because the levels are at most 1. Even here we do not have a right subtree. Here we have a left subtree and right subtree, and the levels are same. Okay, this is our level number 0. This is level 1. This is level 2. Here the left subtree is at level 1. Here we have the right subtree at level 1, but it has a level 2 as well. But the difference is only 1, so it doesn't matter. What about this one? Okay. Actually, for AVL tree, we have to understand a property which is known as height balance property. It means that for every internal node, the height of the children is differed by at most 1, as we just saw in the definition. Any binary search tree that satisfies this height balance property is actually known as AVL tree. So you can see from here the example given in A actually satisfy the AVL balance height balance property. So there is an example of AVL tree. While the tree shown in figure B is not an AVL tree because you can see that some of the nodes have left subtrees whose height are too larger than the right subtrees. Now you can see here the height is much more larger than the height here. Okay. So if that is the situation where the height of one subtree is greater than the height of the other subtree, then that is not an example of AVL tree. I'm sure you must be aware of the height of a tree. If any student do not know what is the height, the height of a tree and the height of a node, if you are not aware with these terminologies, please refer to the tree sections. Inside the tree, we have different terminologies, and one of them is height of a node. Let me revise. Actually, the height of a node is the distance, the length of the longest path from the node to the leaf node. Let's suppose we have a node V. In this case, this is leaf node. A node which has no child is actually leaf nodes. Okay, all these are example of leaf nodes. So the height of this node represented by V, which is 8, it is actually the length of the longest path from this node to the leaf. What is that distance? 1, 2, 3. So the distance from the node to the leaf is 3. Let's suppose V, this is V2. For example, this is V1. Here, the distance to the leaf node or to the external node is only 1. So you see the difference? 3 minus 1 is equal to 2. The difference is more than 1. That is why it is not an example of AVL. Suppose here the V1 is 8 and V2 is 16. This is the leaf node, leaf node, leaf node, leaf node. The distance, the height of this node is actually the longest distance between this node and the leaf. So here we have 2. The height is 2. But here the height is 1. The distance is 2 minus 1 is equal to 1. Okay, at most 1. That is acceptable. So this is an example of AVL. Now see these examples. This is an example of AVL also. Why this is not AVL tree? Let us see. Suppose this is V1. So the height to the leaf node is 0 because it itself is a leaf node. Now this is V2. This is leaf. And this is leaf, the longest leaf. The height here is 2. 2 minus 0 is equal to 2. So the difference is 2, which is greater than 1. So it means this is not an AVL. Same is the case here. This is not an AVL tree. This is also not an AVL tree. These are examples of AVL tree. I hope you will understand. You have understand the concept of AVL tree, which is also a type of a binary search tree. Now let's move to another type of search tree, which is very classic one as well, and that is known as red-black tree. It is a historically popular alternative to AVL tree. You see, first we deal with BST, then one of the drawback, performance in unbalanced tree. We address it with the help of AVL tree. And now another alternative to the AVL tree is red-black tree. Some technical details of the red-black tree are that in the red-black tree, actually in the AVL, a single top-down pass can be used during the insertion and deletion operation. As we do not see the operation, so maybe it is a bit stranger for you to understand this concept. but the approach is actually different from the AVL tree. Actually, in the AVL tree, a pass down the tree is used to establish the insertion point and a second pass. We have two pass, one for insertion and the second pass there to update the height and possibly rebalance the tree. But that is not the case with red black tree. So we can say that in AVL tree, we actually need a careful non-recursive implementation of the tree. We can perform different types of operation on the AVL tree as well as on the red black tree, but we will not go into the details of the red black tree and also the AVL trees, but we will see the definition of red black tree. Actually, it is a binary search tree. Like the AVL, like the BST, it is also a binary search tree where nodes are colored. And there are two types of color that we use, as the name indicate. They are red color and black color. But we have to give these color to the nodes in a proper way so that they satisfy some properties. For example, each node in this tree will be either red or black. And this is sometimes known as color property of the red black tree. Second property is that the root is always black. The color of the root node will be black. Remember, sometime we can omit the rule number second, since the root can always be changing from red to black, but not necessarily the other side. So this rule has little effect on the analysis, and this is sometimes known as root property as well. So generally the root is black, but sometime we can omit this property. All the leaf nodes which are represented by nil should be black, and this property is sometimes referred as external property. Okay, another property is that if we have a node which is red, then its children must be black, and this property is known as internal property. So you see, we have a root property, we have a color property, we have an internal and external properties. Okay, and lastly, every path from a given node V to any of its descendant nil node goes through the same number of black nodes, and this is known as the depth property. Let us see an example of a red black tree. You see, the root node is black here, the root property. All the leaf nodes represented by nil are black, which is known as the external property. Each node is either red or black. You see, we have black nodes and we have red nodes. The color property satisfied. If a node is red, both the children should be black. If a node is red, both the children should be black. Okay, internal property. And then we have the depth property. Every path from a given node, for example V, to any nil must goes through the same number of black nodes. For that we will need traversing of the tree, but we will not go into the details. So this is a general example of a red black tree. Some of the properties we have just seen. The second last tree is known as AA tree. In red black tree we have a limitation, and that is when you perform different operations like insertion, deletion, etc., you will see many rotations are possible inside the red black tree. And that is why sometimes it is a bit tricky to write code to implement the red black tree. In particularly, the remove operation is quite challenging in red black tree, because you have to maintain the property of the depth, the property of the color, internal node, external node, and so on. So AA trees are a variation of the red black trees. It is actually a method of choice when a balanced tree is needed. The AA tree actually adds one extra condition to the red black tree. And that condition is that left children may not be red. Remember, we have just studied a property in the red black tree. Yes, if a node is red, then both the children are black. So here we are actually relaxing, or we are actually imposing another rule, and that is that left children may not be red. So you can see here we have a left children and that is red. We have a left children and that is red. But in case of AA tree, you can see no red children, no left children is actually a red. All left children are black. This is an extra condition to the red black tree, and if this condition is imposed, the desired tree is known as AA tree. So the AA tree follows same rules as red black tree with the additional of single new rule, that is the red nodes cannot be present as a left child. That is the main difference between AA and red black tree. Finally, we have the Splay tree. Actually, it is another way we can implement fundamental map operations and dictionary operation by using a binary search tree. It is another variant of a binary search tree. Here we have to understand one concept, and that is that the recently accessed element is always placed at the root of the tree. So you can define this tree as a self-adjusted binary search tree in which every operation on element actually rearrange the tree so that the element is placed at the root position of the tree. Means every operation is performed at the root of the tree. That is the simple basic concept of Splay tree, that every operation is actually performed at the root of the tree. And we are using a word in the Splay tree which is known as splaying, and this means that the process of bringing an element to the root position by performing suitable rotation operations. By using rotation operation, we actually bring the element to the root on which the operation is required. This structure is conceptually quite different from the other balanced search tree that we have just studied, because the Splay tree does not use any explicit rules to enforce the balance property of the tree. Instead, it applies a certain move to root operation, which is known as splaying, after every access, in order to keep the search tree balanced in a amortized sense. The surprising thing about splaying is that it allows us to guarantee that the running time for insertion, for deletion, and for searching will be logarithmic. So the performance of Splay tree is always logarithmic. And the basic operation is that we have to move the node to the root on which the operation is required. Well, this was a bit discussion about the different type of trees, search trees that we have available. We started our discussion with the very first search tree, which is known as binary search tree. Inside the binary search tree, we saw different operations that we can perform on the binary search tree. For example, we saw how we can search an element in a binary search tree. We saw how we can insert an element into a binary search tree. And we also see how we can delete an element from a binary search tree with 4 different conditions. If the node that we want to delete has no child, if a node that we want to delete has one child, that is the left child, and the third case is the node that we want to delete has a right child. In the fourth case, which is a bit more tricky, is actually the node that we want to delete has both the child. And then we saw examples of each of the case of deletion. We also saw analysis in a brief way the analysis of insertion, searching, and deletion. Finally, we saw performance analysis of the BST algorithm, which is also logarithmic if the tree is perfectly balanced, and is linear sometime and square if it is unbalanced tree. After that, we saw another type of another type of search tree, which is known as AVL tree. We saw the perfectly balanced binary tree definition with example, and also we discussed the height balance property of the AVL tree. And then we saw a bit about how red-black tree are, what are the properties of red-black trees with the help of an example. And after that, to remove one of the drawback of the red-black tree, we saw the AA tree with an extra condition on that we imposed on the red-black tree. And finally, we saw the Splay tree, where the basic operation is to move the node on which the operation is required to the root position and then perform the operation. Okay, I have an assignment for the students. That is assignment number 4, last assignment of the course. And you will see the details about the assignment on the course website. Thank you so much for attending the class. I wish you all the best. Goodbye.